In this video, we are going to continue to study the lock-free singly linked list. So in the last video, we studied the algorithms and the high-level explanations of the synchronizations that is conducted on this sorted singly linked list. And in this lecture, we are going to study a few design choices. So why it is designed in this way. So I'm going to explain a few of them. And also, I'd like to explain why the synchronizations are safe or correct. Why the insertion, deletion, and lookup, even though they are concurrently executed, they are somehow safe and they are working as expected. So the first question is, in the deletion, I explained that we are going to first tagging a node to denote that this is logically deleted, and only after that we are going to delete this node or unlink this load by actually updating the pointer. So why do we do that? I already explained it in the previous lecture video, but I'd like to repeat it because it is the most important design choice of linked list, lock-free linked list. So let me show you this figure here. So suppose that a head pointer is pointing to the first node, and this first node's next pointer is pointing to the second node, and on and on and on. So far so good. And we suppose that we are concurrently deleting the second node here, and also we are concurrently inserting a new node. Let's say this node X. New node X between node 3 and node 2 and node 3. So insertion is easy. We are going to perform a compare and swap on this node. So we create a new node and let it point to node 3, and we perform the KAIST on the next pointer of this node 2 from the original pointer to pointer to the new node. So that is pretty much easy or pretty much expected. It is the atomic way to insert a node between 2 and 3. But in addition, suppose that we are concurrently deleting this node. And suppose that in a naive implementation or incorrect implementation, in order to remove this node, we are immediately updating this pointer to point to this node. So suppose that in a wrong implementation, we are going to perform a KAIST on node 1's next pointer from node 2 to node 3. If it is the case, one of the final results after this deletion and insertion is that head is pointing to node 1, and node 1 is now pointing to node 3. Because in the course of removing this node 2, node 1's next pointer becomes node 3. And node 3's next pointer is node 4, and on and on and on. So in maybe the final result or final memory layout of the singly linked list after this concurrent deletion and insertion. The problem is that node X that is just inserted in here, it is forgotten. Node 2 points to X after this insertion because we perform the KAIST on node 2's next pointer from node 3 to node X, but node 2 is now deleted. It is no longer reachable from the head pointer, and as a result, this node X is just forgotten. That is a problem. Even though this value is inserted, it is not in the data structure. It doesn't satisfy the intuitive specification of a linked list. We should not allow such cases to happen. How to do that? How to prevent such cases? So the logical deletion is a very clever idea to do that. So in deletion of this node 2, we don't update node 1's next pointer immediately. Before that, we are updating node 2's next pointer. So it is currently just pointing to node 3, but we are going to tag this pointer as deleted. So the physical way to do that is that updating the least significant bit of this pointer with 1 using some of what is called fetch and or operation. Okay, so far so good. If this pointer is tagged as 1, let's denote it this way, then insertion will fail because node 2 is marked as logically deleted, and this cast will fail because it is trying to update the pointer to node 3 to the pointer to the new node, and the value inside this node to the next pointer, it is no longer just node 3. It is tagged pointer of this node 3. So the cast will fail because of the tagging. Because of the tagging, the physical value of the pointers will differ. So that's the reason why the cast will fail. And as a result, this insertion will fail after this deletion is successfully logically deleting the node 2. On the other hand, if this insertion is performed first, then node 2's next pointer is now node X, and this logical deletion will fail because it is not going to be the node 3. So the tagged pointer will just this node 2, the pointer from node 2 to node 3 will not be tagged because a new node is inserted in between. And as a result, this will not succeed in logically deleting by tagging the pointer to node 3. So depending on the order of the operations, either one of them happen. Deletion, if this deletion is successfully logically deleting first, then this insertion will fail. If this insertion will succeed, then this code will not logically delete the node 2 by tagging the pointer to node 3. So that is basically how to coordinate this concurrent deletion and insertion in the implementation. So to summarize, so it is the possible end results in a naive wrong implementation, which is very bad because node X is just forgotten. This case is prevented if we add logical deletion. Now, logical deletion introduces a little bit of a complication. The reason is that even though logically a node is deleted from the linked list by its next pointer being tagged with 1, it may still reside in the linked list physically. You can reach the logically deleted node by traversing from the head pointer. So at the end of the day, you need to just remove or unlink the node from the linked list. So that is what should be done in the implementation. So depending on how to or which logically deleted nodes is actually physically deleted. So the three traversal strategies are invented in order to deallocate, unlink the nodes between the logically deleted node. And the three strategies are Harris's strategy and Harris-Michael strategy and Harris-Hurley-Chavez strategy. Okay, so far so good. I think that now you quite well understand why we first logically delete the node and then physically delete the node. The reason is to synchronize with insertion and deletion. Okay, let me move on to the second question. What's the motivation of Harris-Michael's list? So in Harris's strategy, you are going to update the pointer, and you are going to physically unlink multiple nodes at the same time. So if there are two consecutive logically deleted nodes, then in the Harris's strategy, you are going to update the next pointer, and it is not just updating the pointer to the just next one, but it is updating to the next one, effectively unlinking two consecutive logically deleted nodes. So you can think that Harris's list might be faster, and it is indeed the case in our benchmark. Then what is the motivation of this Harris-Michaels list that is just unlinking only one node at a time? So the reason is that the most famous algorithm for memory reclamation for concurrent algorithms, which is called hazard pointers, it only supports my Harris-Michaels strategy. It doesn't support the Harris's strategy. That's the reason why we are not going to, we also learn Harris-Michaels strategy for list traversal. So on the hazard pointers, we are going to deal with it in the later part of this course. And actually, homework 6, the final homework, will be about implementing hazard pointers. And you can then later you can understand that why Harris's list is not supported by hazard pointers, but Harris-Michaels strategy is supported by hazard pointers. So for now, I didn't explain well about this point, but just please memorize this fact. So we are going to deal with this at the later stage of the course. And the final question is, what is the motivation of this Harris-Hurley-Chavich list? So it doesn't physically delete the nodes at all. It just moved on without bothered with the in-between logically deleted nodes. It just go over. The reason is that it doesn't want to wait for the other threads to succeed in some operations. So it is possible that in KAIST you may fail to update you may fail to perform the KAIST. And if it is the case, you may fail to traverse further. And that's the reason why we do Harris-Hurley-Chavich. We are just going to go over without bothered with the logically deleted node. And in that sense, this particular lookup or this particular traversal will be very fast. So if your query is very much important and it should be served with a ultra low latency, then you are likely choosing Harris-Hurley-Chavich strategy because it should run fast. The fixing the list, actually physically deleting the nodes, it can be done by other lower priority tasks. So that's the motivation of this strategy. And so far so good. And now let's move on to the synchronization and the correctness of the synchronization. Why this is correct algorithm on top of the relaxed memory concurrency. So this is basically trying to answer such a question. And here are the reasons here. As usual, like for queue and like for stack, we are going to establish an invariant. Invariant must be maintained by every operation that is concurrently executed at the same time. And furthermore, using this invariant, we need to be able to prove the safety of the operations. So basically, this is the for maintaining and exploiting the invariant. If you are going to write something, you usually want to do with release so that you are going to maintain the invariant. When you are going to read something, usually you want it to be an acquire read because by acquiring it, you want to exploit some invariant. So the same thing happens for this too. The write must be release and the read must be acquire for many places. Okay, the invariant is that at every pointer, it can be a head pointer or the next pointer of a node, etc. Every pointer value has a release view according to the promising semantics, and its release view is bigger than or it is greater than or equal to the messages for the next pointed node's value and its next pointer. So let's look at the figure here. Suppose that a pointer is pointing to some node, and the invariant is that pointer's release view is greater than or equal to the message for nodes.value and nodes.next. So this is written by something, and node.value is also written by something, and that write has the timestamp in the promising semantics, and the invariant is that those timestamp for the message here for the latest value of this node.value and node.next, they must be already acknowledged by the pointer's release view. So that is the invariant. And let's look at the code now and how this invariant is maintained and how this invariant is exploited. Okay, so this is the list implementation, just as we looked at in the previous lecture. And let's search for ordering. So the drop is completely owning a linked list, so we don't need to synchronize with each other. So there's no reason we should use release and acquire. We can just relax here. And in the find heritage strategy, we are going to read the next pointer, the current node's next pointer, with acquire. What is the reason? The reason is that if this becomes the next current pointer, so we are in the traversing this linked list. So we have a previous and the next previous and the current pointer, and at the next iteration of this loop, this next pointer will be the new current in the next iteration. And actually, we are dereferencing the current pointer at this point of time. So in order for this dereference to be sound and it sees the latest value, we need to acquire this pointer. Because this is acquire, we know the latest value on this next node's value and the next pointer. And that's the reason why when it becomes the next current pointer in the next iteration, we are going to safely dereference the current nodes and its key. So that's basically the reason why we need to make it an acquire. So far so good. And a similar thing happens here as well. So the similar thing happens in other strategies. Why this should be acquire? Because we are traversing, and in order for this key lookup to read the latest value, not just the garbage value, we need to make it an acquire. So far so good. And the same thing, the same explanation applies to this acquire as well. And now we are going to explain other orderings as well. For example, in this update of this previous node, we are doing release. So the reason is that we are overriding the pointer value from the previous pointer. So we are pointing to some node in the name of the previous node, and we are overriding the pointer to the current node here. So the previous was this, and it is being updated to point to the current pointer. And we need to do it release because because we want to establish the invariant. The invariant is that this pointer, the new point, this becomes now pointing to the current node, and this pointer value's release view is greater than or equal to the current node's key value and the next pointer. Unfortunately, this is already acquired by the previous iteration of the lookup here. So this next becomes the next current node, and because this is acquired, now it can be released to maintain the invariant of this previous node. This previous node's next pointer, its release view becomes greater than or equal to the current node's key value and next pointer. So to maintain this invariant, we are using the release here. So far so good. And the reason why we should do acquire here is almost the same with the fact that almost same with the the reason why this should be acquired. We are traversing the list, so we need to make it an acquire. Similarly, this should be released because we are overriding the previous node's next pointer from this to this, and we want to release the next pointer's key value and next pointer that has been just acquired here, and the knowledge acquired here should be released to this previous node. That's the reason why it must be released. And similarly, this should be released as well. This and this must be released for almost the same reason. Okay, so far so good. But what is interesting here is that it can be relaxed because we are not going to read the next pointers. So this is basically reading the current node's next pointer, but we are not going to read the next pointer at this point of time. We just want to check the tag of this, the tag value that is written in the next pointer. We just want to know the value of this, and we don't need to access the next the next node. So that's the reason why it doesn't need to be acquired. Okay, so far so good. And that's basically the reason why all the orderings should be acquired or released, or it can be relaxed, etc. And you can read other orderings as well, and their reason is almost the same with what I just described for the finding strategies. So it must be released for the same reason that the invariant should be maintained for the self.prev pointer, etc., etc. So that's basically the reason. And please go through all the occurrences of the orderings and try to explain why it must be released, why it must be acquired, or why it can be relaxed. By doing so, you can easily understand the why this code is correctly synchronizing among multiple concurrent operations. Okay, so far so good. And